In series element matching, what we found was that we can match a characteristic impedance of a transmission line to a load simply by inserting a known length of transmission line with Z0. We know the length of that guy. And then we put some sort of reactive component in series, and that reactive component can either be an inductor or a capacitor. So by choosing the appropriate value of either an inductance and capacitance and selecting a length of transmission line, we can create a matching circuit where the characteristic impedance of whatever length of transmission line this is equal to the input impedance of this entire circuit. The problem with this is parasitics of these devices. Inductors and capacitors at high frequencies are relatively poorly behaved devices that don't exhibit the properties that we would expect. This is for a variety of reasons. In this class, all you need to know is that's the case. Inductors and capacitors don't behave well at high frequency. Fortunately, when designing matching networks, we have an alternative. And if you remember in our discussion for input impedance, that short-circuited and open-circuited transmission lines appear as purely reactive elements, and we control how much reactance by adjusting the length of the transmission line. So we can create capacitors or inductors by using short and open circuits of transmission lines. We'll see later that it's kind of preferable to use open circuits in many applications, although not all. And so both of these are useful techniques. And what that ends up looking like is that we have a load, we have a length of transmission line here. We then put either a short or a open circuit in series with the transmission line, and that we need to calculate the physical length of that short or open transmission line, the L in this equation. And then that creates a circuit that has a Zn of that network that is matched. So overall, the process is mostly the same as what we've already experienced. The difference is that we need to calculate this value of L right here. And to do that, we'll use the short circuit point and the open circuit point on the Smith chart. I really feel that this is best explained via an example, so we'll do that on the next slide. In this example, what I'm having you do is to match a load of 30 minus J50 with a transmission line having a characteristic impedance of Z0 as 100 ohms. So the first step is that we will calculate the normalized load impedance. That's 30 minus J50 divided by Z0, which is 50 ohms, and that gives us the 0.3 minus J.05. So I've plotted that for you right there. The next step is that we need to draw this operating circle right here using our compasses. So same as before. The next step is that we're going to find the 2 points in which the operating circle intersects with the r equals 1 circle. And that point, I've marked one of them there for you. It's 1 plus j 1.56. And I'll mark the second one for you. It's down here at 1 minus j 1.56. And for either of these procedures, I can choose either of those points. For this example, I'm going to continue to use the inductive region of the Smith chart. So the next step is to draw these lines that extend from the center of the Smith chart through the intersecting point and through the normalized load impedance point. So I draw this straight line and I draw this straight line, and what I need to do then is note their wavelengths towards the generator. This is let's see, what is that value? 0.1775 lambda wavelengths towards the generator, and this here is 0.4212 wavelengths towards the generator. That's 0.4212 lambda wavelengths towards the generator. And so what this calculation allows me to do is, if I've got ZL here, I need to calculate how what D is here, the distance from the load to the insertion of the matching element. And that distance is going to be the rotation in wavelengths towards the generator. So this outer scale, which you'll recall is a clockwise rotation, so I'm rotating from this point to this point clockwise. And so I'm going from 0.4212 to 0.4212 and so this rotation, this segment of rotation right here, is going to be equal to 0.5. Remember, that's the one full rotation around the Smith chart is half lambda, so that's 0.5 minus 0.4212, and then the distance from here to here is 0.1775. So that gives me a D of 0.2563 lambda. And so that's the physical length of a transmission line that I need to insert there that has a characteristic impedance of, in this case, 100 ohm T line. So I do that. Now what I need to be able to do is I need to be able to cancel the reactance of J1.56, and I can do that either using an open circuit or a short circuit. So remember that there are 2 points that represent open circuit and short circuit on the transmission line. One here is at the R equals infinity, and that is the open circuit point. And the second is R equals 0, which is the short circuit point. So to determine the length of T line that I would use with an open circuit, what I need to do is I need to measure the distance to the point that cancels this J1.56. So to cancel plus J1.56, I need to come down here to minus J1.56. So I plot that point. Again, that just cancels the reactance of the intersection point right there. And what I do is I'll plot this straight line here, and I'll mark that wavelengths to the generator, and that was WTG equals 0.341 lambda. So that's that point right there. To match with an open circuit, I just need to know the distance from here to here in terms of wavelengths towards the generator. So I go from the R equals infinity point, and we notice that that's got a WTG of 0.25, so the distance from here to here is for the open, which is R equals infinity. We've got 0.341 lambda minus 0.25 lambda, and so that gives us a value of 0.91. And for the short, we just need to rotate clockwise to this point from the short circuit. Well, the short circuit's easy. It occurs at wavelengths towards the generator equals 0. So the distance in wavelengths from here to here is just 0.341 lambda. So that has shown us that there are 2 matching networks that we can develop, either using an open circuit or a short circuit. We've got our load, which was 30, and we've got a 50 ohm capacitor. What we do is we put in a length of T line that Z0 equals 100. That length of T line we calculated as 0.2563 lambda. Then what we did is we inserted our matching element, and that matching element can either be an open circuit or a short circuit. We'll do the open circuit first. So I just put in a length of transmission line there, just like that. The Z0 of this transmission line is got to be equal to 100 ohms, and the length here, the physical length from here to here, L, is going to be 0.91 lambda. And so that's what our matching network is going to look like. And it doesn't matter how long this end of the cable is. This could be 1 meter, it could be 1,000 meters. It doesn't matter. Its characteristic impedance is 100 ohms. And this open circuit in series with all of this here also looks like a Z input of 100 ohms. This circuit would have looked real similar for a short circuit, but instead of L being 0.91, instead of that length being 0.91, what we do is that length is just 0.341 lambda. Okay. So why would I choose an open or a short? Well, in this case, typically what I'll be trying to do is I'll be looking to minimize the length of the stub that's inserted. So a problem might say match the load to the transmission line using the shortest stub possible. That's a very common application. So that's the use of series stub calculations.